In this chapter, we'll learn analysis of variance. This is used to compare multiple populations. Previously, we have learned how to compare two populations with two sample t-test. When we have multiple populations, say more than two, if we have like at least three populations, then this analysis variance method works well. The setting for ANOVA, analysis of variance, is abbreviated as ANOVA. The setting for this contains multiple populations or treatments. Let's say we have I populations, and the first population has mean mu1, second population has mean mu2, and so on. We do not know what is the true mean of each of the populations, but we would like to compare them. This analysis is mostly used to try to compare treatments, and people do seldom use them to denote for population. So you can imagine there is treatment 1, treatment 2, and so on, and we would like to compare these treatments. When the situation is easy, it's pretty straightforward to compare. But in some situations, we have to use formal procedure to compare them. In the formal procedure, we specify a hypothesis, and then we construct a test statistic, and we try to use statistic to decide whether there's enough evidence to support the hypothesis of what we want to consider. The null hypothesis in this case is to specify all the means are identical, so there is no difference at all. On the research hypothesis, we specify that at least two of the means are different. This could be like the first mean different from the second mean, or the first mean different from the third mean, and so on. As long as any of those are different, we will be under the alternative hypothesis. In order to conduct the test, we will need to have a random sample from each of the population that we want to compare. Let's denote the sample as X sub ij. The subscript I tells that it's from the X population, and J indicates that it's the J's observation in that X population. The capital letters is used to refer to the random variable, and the lowercase letter little x ij is used for the observed data. We use the observed data to help us to conduct the test. Generally, we see these data are arranged in a table. One row for one population, like I equals 1, all the data are in the first row. I equals 2, all the data are in the second row, and so on. Here's an example. Like this one, we have different types of boxes, and we would like to compare the comparison strength of these boxes. In the first row, you see there are 6 observations for that first type of box, and you see the sample mean and sample standard deviations listed here. Similarly, in the second row, third row, and fourth row, we have sample from the second types of box, second type of box, and third type of box, and so on. The comparison of the means, first would be looking at the sample means. In this case, we see the sample means listed as 713, 756, and so on. There's one, the last population has a sample mean of 562. This number seems to be obviously different from the other numbers. So in this case, it's not very difficult to make a judgment. If we try to produce a box plot to show the samples we observed, then this box plot will quickly separate the last sample from the first 3 samples. So in this case, we can say that the data provide evidence to say that not all the means are identical. However, in case the data do not have such a distinct separation, for example, If we make the last population, all the observations at 120, suppose there was a recording error in that data and the actual observations, each one should be added 120. In that case, what will happen is that the last sample will no longer be very well separated from the first three samples. So here's the plot after adding the 120. You can see that these box plots start to overlap, and therefore it's difficult to tell whether they are really different from each other or they are what you see. The slight difference is simply because of random variations. So in order to perform a test, let's use the following notations. We already mentioned that the X with subscript INJ, we use it to denote the sample or observation, depending on whether it's capital letter or lower letter. And if there's no ambiguity, we would just directly use subscript I and J without a comma. If, for example, you do have observations like the 12th observation, 15th observation, in that case, it's good to use comma like x1, comma 12, so that it's not confused. We would assume that these samples for the same population, they are randomly distributed and they are identical. We used to call that a random sample. And for the different samples, they are from different populations, we will assume that these different samples are independent from one another. In some situations, the number of observations from in each sample is equal. That's a situation that is relatively easier to understand. We will talk about the equal sample size case. When the sample sizes are different, there are different formulations for the test. Say in the equal sample size case, what we want to compare are the different treatment means or population means. And these population means, if the data are normally distributed, we have learned in the point estimate that chapter that the average is a good estimate in the sense that the average from the sample provides a maximum likelihood estimate of the population mean. So in this case, we have multiple populations. Therefore, we use the average of the sample from that population to estimate its mean. Like X bar 1 is the average from the first population. It should be X bar 1 dot, X bar 2 dot, and so on. So those are sample mean for that each population to estimate the population mean in that population. Beyond that, in the case when all the populations are identical, in that case, the means would be equal. If that's the case, then we can average all the observations. So that gives us this grand mean, X bar dot dot. The grand mean of the sample provides a MLE, maximum likelihood estimate of the population overall mean. So basically, in order to test the hypothesis, we'll try to consider the comparison of the mean estimate in each one of them and the overall mean. Simply just compare the two alone is not desirable in the sense that we have multiple treatments. If we try to look at each one, like X1 bar, X bar 1 dot versus the overall grand mean X bar dot dot, we would have I of those, but we need to combine all of them together. So how do we combine them together? One way to do that is to consider the different variations, different ways of estimating the variations. So here comes another assumption. This assumption says that all populations have the same variance. In that case, we can use sample variance to estimate the variance. S1 square, that's used to denote the sample variance from the first sample. S2 square is the sample variance from the second population, and so on. from second sample. And for each of these sample variance is estimating the same common sigma squared, the identical variance. Then we could combine these sample variances together to give a single estimate of that variance. So how do we do that? We make an assumption that the variances are the same. And then we use the observations here, this part, S1 squared plus S2 squared and so on up to the last one. All of the sample variances, we average them. So that gives us a term that's called the mean squared error. The mean squared error is really the sample variance estimate, but being averaged across all of the populations, all of the treatments or the samples. Beyond the mean squared error, we could also come up with another way of looking at the variation. Since the sample mean from the first treatment, for example, x bar 1 dot minus x bar dot dot, that tells about the variation of the first sample average compared to the grand mean. We could look at how much variation that one is. In particular, if the x bar dot dot is really truly estimating the common mean, then this x bar 1 dot minus x bar dot dot is having a mean of 0, and the variance is equal to the sigma squared over the sample size in that first population. Similarly, x bar 2 dot minus x bar dot dot would also have variance equal to the same sigma squared over the sample size. So for that reason, if we multiply this sample size, the common sample size j here, j multiply this squared deviation from each one of them, that will give us one measure of variation of this sample mean estimate compared to the grand mean. And then we divide it by the number of, here the I-1 is the degrees of freedom. We have I-1 rather than I, that's because the grand mean here is used as to estimate the common mean. Therefore, the x bar 1 dot, x bar 2 dot, and x bar I dot, we only have I-1 of them being free. So this term shown on the slide is shown as MST, meaning that the mean squared for treatment or mean squared for the population. It provides another estimate of the population variance, common population variance. So basically, this test will be done based on comparing these two different estimates of the population variance, MST and MSE. The MST measures the variation of each of the sample average compared to the grand mean. On the other hand, the MSE is a measure of variation of within each of the sample. So because the sample variance is computed based on how Xij observation deviate from its center, x bar I dot. So this MSE gives us an estimate of the variance regardless of the mean being equal or not, but the MST, the treatment part, would only give us the estimate of the variance when all of the means are identical. What will happen when the means do not have identical, when mu1, mu2, and so on are not identical? So if the means are different, then the xi's, they estimate the mu I, they will also be different. And once they are different, when we subtract the x bar dot dot, that will spread out more. Therefore, we have bigger deviation for each of the, consider all of the x bar I dot sample mean from x bar dot dot will have a bigger spread compared to the case that when they are all having the same mean. So under the null hypothesis situation, the x bar I dot and x bar dot dot, they're all estimating the same mean. Therefore, the divisions of x bar I dot and x bar dot dot should not be too big. So that makes the contrast between the two scenarios. So we will use the MST under the null hypothesis to help us to decide whether this null hypothesis is true or not. When the null hypothesis is true, an important fact is that the mean squared for treatment and the mean square error, both of them, if we calculate the expected values, it will be equal to this common variance. On the other hand, when the means are not identical, in that case, because x bar I dot is different from other x bar, different from the x bar dot dot, so we have bigger variation. Therefore, the expected value for the mean square of treatment in that case is bigger than the mean square error. We'll take the ratio of the two because as you see, when the null hypothesis is false, the mean square treatment is bigger, tend to estimate something bigger than the sigma squared. So we will look at the ratio of the two to build the statistic. In particular, this ratio will define it as the F. And what is this F here? F will give us the MST over the MSE. So here is a little bit of computation of the MST for an example. And this example is the same one talking about the 4 different types of boxes. And 713 is the average from the first types of box, and 756 is from the second type of box, and so on. 682.5, that's the overall average, the grand mean. And in this calculation, you see the squared differences and multiplied by 6 divided by the 4 minus 1. This computation will give us the mean square for treatment. And for the mean square error, it's each of the observation minus the mean of in that row. And then afterward, we take square and divide it by the total number of free values in there. What's the total number of free values? In this case, it will be the I times j minus 1, because there are I treatments, and for each treatment, we have the xij minus the x bar I dot. And this x bar I dot is estimating the mean. And once you have the mean of it fixed, there are only there will be one less of the observations. One less degrees of freedom. So if we have 5 observations, then the degrees of freedom becomes just 4. Okay. In fact, for this case, we'll look at the degrees of freedom in just a little bit. What is the degrees of freedom? Is this I times j minus 1. J minus 1, that's from one treatment or one population, the sample size in one sample. And then we have I samples, so the total number of the free elements that we have is I times j minus 1. That's the degrees of freedom for the MSE. And the one for the mean square for treatment degrees of freedom is I minus 1, because we are looking at these I of the averages compared to the grand average. So it's I minus 1. And for the test, we simply compare the MST and the MSE. This comparison was based on the MST divided by the MSE. Generally, if these two are close to each other, we would believe that the null hypothesis, there's no evidence to reject the null hypothesis. On the other hand, if MSST over the MSE is much bigger than 1, then that gives us evidence that the null hypothesis is false. In this one, if you look at the MST, it's 42,000 something. MSC, on the other hand, is 1691. The ratio is much, much bigger than 1. Okay, so how big is this ratio? In fact, the ratio, if you try to compute it, is about 25. And with the 25, we need to, we already, based on like the overall simple thought of much greater than 1, and we will know that this provides evidence that null hypothesis is not true. But if it is closer to 1, then we will need to give a formal way of to figure out how to summarize this evidence. We are going to use the ratio as this test statistic, and for this ratio, we need to know its distribution and use it to compute the p-value. So p-value in this case, it refers to this ratio when we treat it as a test statistic, MST over MSE, mean square for treatment over the mean square for error, okay? This ratio has F distribution with numerator degrees of freedom equal to the n-1 and denominator degrees of freedom equal to I times j-1. Once we know the F distribution, then we will be able to use that F distribution to give us the p-value. P-value refers to the probability of probability of observing more extreme case of the computed statistic when the null hypothesis is true. In this case, the extreme would refer to the ratio is even bigger than the calculated one. So we look at the F distribution greater than the observed. Let's call this observed F as the little f, written as lowercase f. So as long as this probability in the F distribution greater than this observed F is small, we would reject the null hypothesis. So in this case, this quantity computed is 25, and we try to see with this 25, how big is the p-value? From the F distribution, we simply, if you compute it in R, it's 1 minus PF. And that tells us the p-value. For this case, we provided the degrees of freedom of 3 and 20. So once you put in the 25 and the 3 and the 20, 1 minus PF give us the probability to the right of 25.09. And this is the p-value. This p-value 5.5 is very small, then it tells that we have strong evidence against the null hypothesis. Therefore, we would conclude that the compression strengths are not all the same for these 4 different types of boxes. So that's if we use R to do the computation for p-value. 1 minus PF give us p-value, okay. If you do not use R to do the computation, then you can compare this value to the critical values in the F distribution table. Table A9 gives the critical value, but unfortunately for this degrees of freedom, we have 3 and 20 as the degrees of freedom. The largest critical value with these 2 degrees of freedom is at 8.1. Our observed value is 25, much greater than 8.1. Therefore, we would know that this probability of to the right of 25 is even much smaller than the probability to the right of 8.1. And for 8.1, the probability to the right of that is 0.001. So with this table, we can only tell that the p-value is smaller than 0.001. but it could not tell you what's the exact value of the p-value. When we used R, we were able to calculate this exact value of the p-value. This notation 5.5 e minus 7 means 5.5 times 10 to the power of negative 7. So that's a very small p-value. If you have a significance level like 0.001, even 0.0001, you would always reject because p-value is less than that significance level. Okay, so that's for this example. To conduct the test for this example in R, we can read in the data, like here, read.csv to read in the data. And then afterward, we use lm command to build this model. What's in the model? Left-hand side, that's a formula. The formula left-hand side gives strength. That's the variable that we want to compare. And the right-hand side of the formula, right-hand side of tilde, that designate what variable is specifying the different populations. In this case, it's the box type. For this particular data set, the box types are recorded as 1, 2, 3, 4. If we directly put the box type there, we'll have wrong answer because 1, 2, 3, 4 will be treated as a continuous variable. So instead, we need to specify factor with the box type. And once we use the factor, then we will get the correct output. To see the output, you use the ANOVA command with this model object. So I'll put ANOVA and MOD here. It gives me this table. And in this table output, you see different stuff there. One is saying the factor box type that basically tells that this variable that help us to tell what are the different types or different populations. That's for that variable, how many degrees of freedom, that's the 3. 3 is equal to the number of different levels of that factor minus 1. And this sum SQ means sum of squared. And min SQ means the mean squared. Mean squared, here min SQ really is the quantity that we call the mean square for treatment. And in the next row, we see the residuals and degrees of freedom. Here, this residual simply refers to the error part. And sum of square is sum of the square error. Mean square is the mean squared error. 1692 mean square. This one listed under the residual is actually the MSE. And the ratio of the previous mean square with this mean square for error is given under the F value. That's our test statistic. And then in the last column here, what we see is the p-value. It's to the right-hand side of this F value from the F distribution that has degrees of freedom 3 and 20. Okay, so that's the output from the R code. This slide just to emphasize that, remember, when you have a variable that you really do not mean it's a continuous variable, then you need to use a factor to designate that's a variable, a categorical variable. As you see, when we consider the test statistic, we are looking at the squared deviation under 2 different scenarios, and we are making assumption that the variances are the same. And only if variance is the same, then the 2 different ways of estimating the variance could be compared. So that assumption of common variance has to be checked to make sure it's correct. One way to check that is to look at the sample standard deviations from each sample. For example, in the 10.1, we have a sample standard deviation of 46.55 and so on, and the smallest is 37.2. If these different standard deviations, the largest one versus the smallest one, that ratio is less than 2, we basically can believe that it's comfortable or reasonable to assume variances are equal. So this is just a rule of thumb, okay? If the largest over the smallest standard deviation is not much more than 2, then we just go ahead to assume variances are equal. How do we check the common variance assumption in R? Here it's the R code to do that. We first specify the model, which is through the LM command. LM means linear model. Strength as a factor, strength as a function of the factor for box type. And then to get the plot, we use this plot command with the model object, MOD. And this plot itself, by default, it will produce 4 different plots, but only 2 of them are relevant to us. And those are the first and second plot. So we specify which equals 1 to 2. The first plot shown here is the residual versus fitted value. Basically, it's just the xij minus the x bar I dot. That's the deviation of each observation compared to its mean in that sample. You can tell here, for those around here, that's one of them. And these from here, that's from the second, and that's from the third and fourth, the last one. So these are basically the residues for the first sample, the xij from the first sample minus its sample mean. And here's the one from the second and so on. Oh, actually, I'm sorry. The smallest one is from the fourth sample. Okay. So from here, we try to see these points, how much they are spread out. These 4, when we compare them, the spread out seems to be not very different. This is earlier that we'll say largest standard deviation compared to the smallest standard deviation is not more than 2. The second, the right-hand side plot is the QQ plot. QQ plot try to assess whether the data come from normal distribution or not. In this case, we are not really making a QQ plot for each sample. That's because in each sample, we only have very few observations, 5 observations. If we try to plot a QQ plot for that, it's highly inaccurate. So we need more observations. And this QQ plot is constructed by considering all of those xij's. So here, xij subtract the x bar I dot. In other words, for each observation, we subtract its sample mean. So that gives us this observations deviation from its mean. And then we simply combine all these deviations from all the samples and then plot it using the QQ norm. Okay, so that's what you saw, this plot. It's the xij minus its own sample mean being plotted against the quantiles from the normal distribution. And how do we decide whether the normal distribution is suitable or not? Recall, back then when we learned it, we try to judge based on whether these points are on a straight line or not. If these points appear to be on a straight line, then we believe normal distribution is suitable. So in this case, we have a pretty strong support that the normal distribution is reasonable. So we considered how to check the assumptions of constant variance and also the normality assumption. In some situation, unfortunately, both or one of these 2 assumptions could be violated. If that's the case, we cannot simply proceed with this ANOVA. Now, when the constant variance is still correct, if constant variance is still correct, okay? In that case, the procedure that we learned here in this ANOVA using F statistic, the F ratio, is still approximately correct if the sample size is large. On the other hand, if the sample size is not large, then we cannot really use that F test anymore. What test can we use? There's a separate chapter about non-parametric tests. The Kruskal-Wallis test would be suitable in this case. If the constant variance is violated, regardless of small sample size or large sample size, then the ANOVA procedure and the F test would no longer be valid. Okay, so earlier when I talked about the test and also the output from R, that involves the column of the sum SQ, and that refers to the sum of squares. Sum of squares simply are just the, if you look at the definition here, xij minus x bar dot dot. This is talking about the squared deviation of every observation compared to the grand mean. We call that the sum of square total, or total sum of square. And the next one, x bar I dot compared to the x bar dot dot, that's the squared deviation of the i's sample mean compared to grand mean. And this one is taking over all of the observations, then we call it the sum of square for the treatment. And then the next one is that the xij deviate from the sample mean x bar I dot, square the deviation of that. That's the sum of square of the error. Okay, so if you look at these sum of square for treatment, sum of square for error, they are really just the mean square for treatment times the degrees of freedom. And then similarly, the SSE is the mean square error times the degrees of freedom. Okay, but a message here is that the sum of square total SST is equal to the sum of square for treatment plus the sum of square for error, the two together. So in other words, when we look at the overall deviations of our observations compared to the grand mean, that variation or deviation, squared deviation, can be decomposed into two parts. One part is because the different treatments might have different populations, might have a different mean. The other part, on the other hand, is simply how is the observations deviate from its own population mean. Okay. And the MST, sorry, mean square for treatment and mean square for error, I just mentioned, is simply just the sum of square quantity divided by their corresponding degrees of freedom. And our F statistic is simply just the ratio of the two. And the table that we saw for the R output is simply this table. The first row is for the variable for population or for the treatment, whatever that you listed. If you give a variable on the right-hand side, this generally we use the name of that variable. And the degrees of freedom for that is the number of populations or number of treatments minus 1. And then this is the sum of square for treatment. And the next row gives the mean square for treatment, simply is the sum of squares divided by its degrees of freedom. And the next line here is recorded as error. Some in R is noted as residuals. Both errors and residuals refers to the part that cannot be attributed to the model. So instead, it's just the, regardless of what is the treatment mean, you are looking at the observed observation minus the estimate in that sample. So this is the part that's in the error. It could not be attributed to the difference in the mean. Okay. And this sum of square error divided by its degrees of freedom gives us the mean square error. And in the last column, you see the little f, that's the ratio. Ratio gives us the F statistic. And if we put the total degrees of freedom from the previous two rows, that give us the total degrees of freedom, which is equal to ij minus 1. This ij minus 1, imagine when we have j observations for each treatment and we have I treatments, therefore total number of observations is equal to ij. But when we look at the total variation, we have each of observations subtract the grand mean. Because of a single grand mean there, therefore the total degrees of freedom is this ij minus 1. And this is the ANOVA table. We have seen the ANOVA table for the examples, and that ANOVA table is obtained by the ANOVA command in R. Here's another example for doing this analysis variance. So here we are trying to consider the fracture toughness of some materials. The fracture toughness, okay. And here we have three different populations. And in fact, these populations refers to the distance to the center of the specimens. The distance from the center of the specimen's base. Anyway, these are the 42, 36, and 31 millimeter. Those different distances are for referring to the different populations. And then we have observed data from experiment. So 4 observations for each of the treatment here, and then we try to compare these. If you look at the average on the last column here is giving the sum rather than the average. If we divide it by 4 on each of the value in the last column, that will give us the sample mean. By looking at those numbers, you already see that they seem to be different. But once divided by 4, yeah, might still be different. So null hypothesis in this case is mu1 equals mu2 equals mu3. And the alternative hypothesis would say at least 2 of them are different. And when we conducted the F test, we could provide the FP value and use it to decide mu1 equals mu2 and equals mu3. But as we know, the test relies on assumptions of constant variance and also rely on normality assumption. So we'll check the constant variance and check normality assumption. For the constant variance, we look at the sample standard deviations. In this example, the values of the sample standard deviation are 0.322, 0.167, 0.278. And these, the largest versus the smallest is not much over 2, so 0.322 over 0.167. That ratio is not much bigger than 2, so we would believe constant variance assumption is reasonable, is okay. And for the normality assumption, we use the combined the residual, which is observed xij minus x bar a dot. Combine all of them together to produce this use the QQ norm to produce this probability plot. And in this case, you see the points are pretty close to the straight line. Therefore, normal assumption is reasonable. If you want to do manual computation, this would be the sum square for total, sum square for treatment, and sum square for error. But we're not going to do hand computation. In case you did conduct the hand computation, then you would put them into this table and then use those sum square from the different source divided by its degrees of freedom. In this case, the degrees of freedom for the treatment or the population, we have 3 populations, 3 distances. The degrees of freedom is 3 minus 1, therefore it's 2. And the error here, degree of freedom, is the I times j minus 1. I equals 3, j equals let's see, j is equal to 4. So j minus 1 gives us 3. 3, and then there are 3 treatments, so 3 times 3 gives us 9. That's the error degrees of freedom. The 2, the 9, and the total give us 11. And the sum of square, the first two add up would be equal to the third one. And then the mean square is simply equal to the sum of square divided by the degrees of freedom. For example, 3.3826, that's the 6.7653 divided by 2. And then the 0.0696, the next row here, that's from the 0.6267 divided by 9. And then mean square, when we use the tool, the one on top divided by the one on bottom, they give us the F test, the F statistic. So in this case, 48, that's a very large value for F statistic. So the p-value is very small, close to 0. If you try to compute all these in R, you can simply first read in the data set and then use the LM command. The left-hand side of the LM command is the variable that you want to compare. And the right-hand side of the tilde is the variable that tells separate different populations. And we specify data equals that data set so that these two variables can be recognized. ANOVA table is obtained with this ANOVA command with the model object. And then we want to produce the two plot to check assumptions. In order to do that, here I'm using the PAR command, specify MF row C equals 1 and 2 in parentheses. That is to specify that I want 1 row, 2 columns for the plot. MAR is to specify how big is the margin in each of the plot. 4 is for the bottom margin. Second one here, 4 again, is for the left margin. 2 is top margin, and 1 is the right margin. And then when I call this plot command, these two will be placed side by side, one on the left, one on the right. You might also want to check the sum of variances. To compute the sum of variance from each sample, we use tapply command. And here is the observed data, the load in this case. And the next is the distance. Distance is the factor that we use to separate the three populations. And then this ST is the command to tell us what do we want to compute. So for each of this distance, it will compute the standard deviation using the load data. So the output, in this case, for analysis of variance table, that gives this one as same as the ones we saw earlier. Now this p-value gives a number 1.5 times 10 to the power of -5. If you look at the two plots, the residual versus fitted again is simply Xij minus the sample mean of that population. We simply look at how much variation are these in the same compared to those in the second and those in the third. If these variations do not seem to be differing too much, that gives us some evidence that the variance seems to be constant. And for the normal QQ plot, we try to see whether these points are on the straight line or not, close to the straight line or not. In this case, a little bit of those at the bottom are not really on the line. So there's a slight sign of the normality assumption may not seem to be reasonable. But in this case, we also know that the sample size is really small. For a normal QQ plot, when the sample size is too small, the plot may not be accurate enough. So that's about this analysis of variance. So for this example, a non-parametric test that does not assume a distribution might be more suitable. Okay, that's all about the analysis of variance. To summarize, what we learned in the analysis of variance is to compare multiple treatments or multiple populations. How do we do that? we collect data for each population, and that's give us a sample. When we have multiple populations, we collect one sample from each population. And then afterward, we try to look at the mean square from treatment and mean square from error. These two different sources of variations. Compare them. The statistic is the ratio between the mean square of treatment and mean square for error. That's the F statistic. And the p-value is the probability to the right of that observed F ratio from the F distribution. And this F distribution has degrees of freedom equals the numerator degrees of freedom and denominator degrees of freedom. The numerator degrees of freedom is equal to the number of treatments minus 1, and the denominator degrees of freedom is equal to the number of treatments times the number of samples minus 1. And to conduct the analysis of variance, we can easily use R to get that. Simply use the LM command to build the model, use the ANOVA command to give us the analysis of variance table. And then we use the plot command to help us to produce a plot for helping us to check the constant variance and check the normality assumption. So that's all for this analysis of variance chapter. If you have more than one of the factor, here we consider the one treatment, different treatments or multiple populations. Sometimes you might have one variable, for example, gender, that gives us male and female. And beyond that, you also have another variable that will separate the population. For example, beyond the gender, suppose you also have age group, and you're looking at the elder and mid-age and teenager, these three different populations. In that case, the related population is a combination of both the gender and the age group. So you have two factors. One is age, the other one is gender. So in this case, when you try to build the model, then only a slight modification is needed to conduct the analysis of variance. What's needed is right-hand side currently has just factor of one variable. When you have multiple of them, you would do factor of gender plus factor of age group, and then plus the product of the two factors. You can also make it easy, simply just write a factor of gender multiply factor of age group. This multiplication in the right-hand side formula really means that it contains both the main effect of each variable and how they interact with each other, that interaction. Due to the limited short period, we're not going to cover multi-factor ANOVA, but the principles is very similar. Okay.